So I'm BURAK, and if you give me yeah. So my research areas are multi-scale modeling, fracture, specifically hydrogen embrittlement, and my research question are, can we control the mechanical properties of engineered materials operating in extreme environmental conditions, and knowing such behavior, can we design more resilient materials, especially for hydrogen embrittlement. Speaking of hydrogen embrittlement, this is multi-scale modeling schema. So mostly the interaction between hydrogen and dislocation is responsible for hydrogen embrittlement. So we need to really understand the atomistic origin of hydrogen embrittlement. Therefore, we need to go deep into the microscale. You can do like some crystal plasticity or phase fields, and mostly we do discrete dislocation dynamics. And two of the most vital inputs for discrete dislocation dynamics are the mobility law and the stress equation. The mobility law for hydrogen embrittlement. So we really don't know whether hydrogen really impedes the dislocation, like slow down speed, or it can shield the stress field of dislocation and increase the mobility of dislocation. Then we need the mobility law. Mobility laws can be derived from molecular dynamic simulations. So at this scale, at atomistic scale. So we performed several MD simulations just to capture the effect of hydrogen on the mobility law of edge dislocation. So in the literature, there are some studies that reveals the mobility law of both edge dislocation or screw dislocation, and these are the studies. Mostly, the phonon drag is the main mechanism of edge dislocation, so there is no thermal activation. But for screw dislocation, they are thermally activated. So edge, like FCC, it's like straightforward. And the mobility law for edge is just shear stress times the Burgers vector divided by the direct coefficient. And the direct coefficient is just a function of temperature. So this is just edge. It can be activated at really low temperatures, maybe 5 megapascal, 10 megapascal. Since it is not thermally activated motion and it's only a phonon drag, the speed of edge dislocation is inversely proportional to the temperature. And here is the mobility law of 110 and 112 in alpha iron. So the motivation of our study is just to find the effect of hydrogen on these mobility laws. All right. So yeah, the aim is just to find the effect of hydrogen on mobility. So we performed several simulations at different stress levels, at different temperatures, at different hydrogen concentrations. And lastly, we came up with several phenomenological mobility laws for edge dislocations. So basically, this is our MD schema. We apply the shear force. The back size is like 30 nanometer, 20 nanometer, 28 nanometer. And we perform the MVE ensemble. So the simulation time is basically 1 nanosecond. But in between, so during this period, we have many pieces of MVEs. And in between these MVEs, we periodically adjust the volume and temperature to keep the temperature and pressure for the prescribed values, very near to prescribed values. So you can also call it MPT ensemble. So we use periodic, and shrink-wrapped boundary conditions. Hydrogen distribution is random. Of course, you can do grand canonical Monte Carlo and put a more realistic hydrogen concentration to the core, like we listen from the professor. But for this study, we perform random distribution. The whole simulation time is 1 nanosecond, and the time step is 1 femtosecond. I think it's enough time step because we also monitor the energy and it becomes steady. So if the energy is steady, your time step is just fine. All right, so we didn't do like the unit step function while given the shear force. Basically for 0.5 nanoseconds, we increase the stress. Then at 0.5 nanoseconds, the stress becomes steady, just not to create some shock waves in the lattice. So this is the way we input our shear stress. So this is just one example at 100 Kelvin for pure iron and with different hydrogen concentrations. Then we observe the displacement versus time graphs. So once we increase the stress, of course, we get more displacement. Once you derive these curves, once you get the first derivative of displacement, you'll get the velocity of dislocations. And these are the stress versus velocity graph of pure cell iron and hydrogen-induced lattice at 50, 100 Kelvin, 200, 300, and 400. Mostly, once we increase the hydrogen concentration, we are impeding the dislocation. We are slowing down the dislocation, like we are decreasing the velocity of dislocation. Then the next step is derive the mobility laws. Here in our calculations, the velocity is tau applied minus tau critical. So this is the critical stress that activates the motion of dislocation times the Burgers vector divided by direct coefficients. But here, direct coefficient is not only a function of temperature, but also the hydrogen concentration, right? So we have direct coefficient as a function of both temperature and concentration. Once you plot this with respect to temperature, we get more or less linear lines. So it is like a linear, we put linear line equation like y is mx plus n. Here, B0, the constant is also a function of C. We don't know it's linear or polynomial, but it's a function of C. And also, the B1 is a function of C plus the temperature. So this is just the equation of line. Then we plot B0 as a function of C, and we saw it's a line, so it's just B2C. And once you plot B1 as a function of concentration, again, a line equation, B4C plus B5. How about the critical stress? Again, once you plot the critical stress as a function of concentration, you'll get a line equation, A0T plus A1T. Once you plot A0 as a function of temperature, so we didn't get the line equation, therefore we assume this is a constant and we get the average value for A0. For A1T, we assumed it's a linear line and we perform the linear line analysis like A2T, A1T is equal to A2T plus A3. Then we got the numbers and we come up with the phenomenological mobility laws for 110 and 112. The Burgers vector is always for BCC, it's 111. For FCC, it's 110, and the planes are 111 but for BCC, the Burgers vector is 111, and the planes are, we have 3 different planes. And here, one can calculate the velocity of dislocation at different temperatures and at different chemical concentrations. So you can do interpolation in between these values. Extrapolation might be difficult, so maybe you cannot go beyond these values like 0.5 hydrogen concentration, but anytime you can do incorporation because you might see different dislocation activities at greater temperatures or hydrogen concentrations. And I have one just schema that represents we have an iron hydrogen system. We have two different dislocations. We performed MP at different stress, temperature, and hydrogen concentrations. We got the stress, displacement, and velocity graphs, and we derived the phenomenological mobility laws. And this is all I have for today for you. And we'll be glad to answer your questions.